we looked at last class. Okay, what did we talk about? Forget about the very first introductory lecture in vector spaces. Okay. Okay. What are vectors? At least in the context of whatever we've seen so far, what are vectors? That's okay. That's big enough. Yeah. Okay. All right. Oh, I'm not. Sorry. Okay. What are vectors? Yeah, ordered. At least for now, it's an ordered list of numbers that we prefer to write it like this. But later on, we'll see you can also write it like this. But we will stick to this convention for now. Okay. The order of the numbers matter, and we are primarily going to be dealing with vectors of finite size. What is the size of a vector? What does it mean when I say size? Right, the number of elements. Okay. And then what else did we look at? And where do the elements, individual elements of the vectors come from? Yeah, these for now these are numbers, and these in the context of what we will look at in this course, they're usually real numbers or complex numbers, mostly real numbers. Okay, and then what else did we look at? Right. Okay, we looked at some types of vectors. We looked at what is the unit vector. What is the unit vector? Let's say EI. This is from Rn. What is this? Right. Everything is 0 except for the ith element, and then you have the 0 vector, 1 vector, and these are vectors that we might commonly come across. And then, all right, we looked at 2 operations, right? 2 operations that we could perform on vectors. One was scaling. What is this? What is vector scaling? Right. So, if you have a vector v, if you multiply it by a scalar alpha, what do we do algebraically, and what do we do? What is the corresponding geometric interpretation of this? Right. In geometric terms, if you have a vector v and you say you're scaling it by a number alpha, you're either stretching or compressing it, and you can also you're also allowed to reverse the direction. Okay, but the direction remains the same. Scaling operation never changes the direction of the vector. Right? That's the geometric interpretation. What do you do algebraically, or sorry? Right, each element. So if you do alpha times e, you essentially multiply each element by the scalar alpha. Okay, that's vector scaling. And the second operation. Okay. And what do we do here? So the scaling operation takes only one vector as its input. Okay, this addition takes 2. And what do you do algebraically to add 2 vectors? Right. Let me call it W. So you simply add the corresponding elements. And what is the geometry associated with this? So if V and W are these vectors, and where is U plus W? So you form a parallelogram of these 2 vectors, and then this would be your. Okay, all right. So those are the 2 operations that we looked at, and then right, and then we started talking about what is a vector space? Right, it's a set. Okay, set of what? Okay, okay, and no, it's not that it follows vector addition, right? Right. So it's closed. Yes, please. Under vector scaling. And what does it mean to say it's closed under? What does it mean? Let's say this set is V. What do I mean by the set is closed under vector scaling? Right. Now, if you take any vector V that belongs to, again, if you don't know what this means, you simply replace this by belongs to. Okay. If you take any vector V that belongs to this vector space V, and you perform some scaling operation on the vector, this will also belong to V. If it does not, then the set that you started with is not a vector space. Okay, that's what it means to say that this is closed under vector scaling. And vector addition is similar. If you have two vectors V and W that belong to this set, and if you add these two vectors, and that also belongs to this set, no matter what U and W you choose, then this set is closed under vector addition. If both of these are satisfied, then this set of vectors can be called a vector space. If any one of them is not satisfied, then it's not a vector. It's not a vector space. Okay. All right. This has some consequences. So one thing is this vector space will always have the zero element, the zero vector. Okay. Now, before we proceed to the next topic, right? Let's look at some examples of what sets might be vector spaces and what might not be. Okay. Okay. Let's say I have a set B. That is, set B is simply the set of real numbers. Okay. Is V a vector space? Yes. It could be yes or no. If you choose any answer, you have to tell me why. You have to argue as to whether or not you argue for your answer. Why is it a vector space?
Because if you scale any element within
right.
it would still be a real
right. You take a real number. Exactly. Yes, exactly. You take any real number, you multiply it by another real number alpha, it will still remain a real number. That means it's closed under vector scaling. If you take any two real numbers, add them, you still get a real number. And so it means this is also closed under vector addition. That means this is a vector space. What is the size of vectors from this vector space? If you take any vector from this vector space, what is the size of that vector? 1, no? It's only one real number. What about R2? So instead of taking one real number, I take, is R2 a vector space? Yes, the same thing applies, right? Because vector scaling simply involves multiplying each individual element by a number alpha. Vector addition involves addition of the individual components. That means both of these will result in real numbers. That means any scaling or addition that you do will always result in another vector where the two elements are real numbers. That means it's from R2. That means it is closed. So that means that's a vector space. Okay. What about this? B is a set of vectors like this, A, B. Okay. Or let me write it, and then A comma B are real numbers, and A comma B are greater than or equal to 0. Okay. I'll explain what that means. So V is a set of numbers like this. A and B, and when you see, and usually when you write the definition of a set, you place it in between two curly brackets. That means what this means. Whatever is within this is a set that you're dealing with. Okay, and whenever you see a vertical line like this, that simply means you can simply read this as such that. Okay, so this set V is a set of two variables A and B such that A and B are real numbers and A and B are greater than or equal to 0. Okay. Now is this set of vector space now? See, when you are confronted with a question like this, you either show a proof that it is a vector space, or you find one example where one of these conditions is not satisfied, and then it's clear it's not a vector space. So the point is, if you try, you of course you can either prove that it's a vector space if it is. If you're not sure, can you come up with an example where if you take an element from here, you do scaling or addition operation, and that resulting vector is not in the set? Yeah. Okay, let's maybe look at the geometry, right? So, this set of vectors V is R2, right? All of R2. What about this set? Where is this set located? In here, in the first quadrant. So it's here. So V is a set of all points in the first quadrant. Now the question is this closed? If you choose any element here, any vector that belongs to the first quadrant, is it closed under vector scaling and vector addition? It is? Sorry? Exactly. It's closed under addition. So if you take any two vectors here, you add it, it will always remain in the first quadrant. You can prove that. Okay. I'll not go into how to prove it algebraically. We'll just leave it at that. Okay. You can intuitively see that if you have two vectors that you take from here, the parallelogram law of addition will ensure that you are in the first quadrant. But the first property is not satisfied, because if I take a vector here and I multiply it by -1, it's here. I get a vector that is not in the first quadrant. That means that is not a vector space. Okay. I hope that, yes.
By the unit in the first quadrant itself,
So you take vectors. Yes. So the vectors come from the first quadrant. The alphas need not. The alpha can be any real number. Okay. Okay. All right. I hope that at least gives you some idea about how you'd go about determining if something is or is not a vector space. Okay. Now, when we talk about sets, right, we also talk about the concept of subset. What is a subset of a set? Right. So if you have a set A, and I say B is a subset of A, what do I mean?
the elements of B are basically from.
Right. All elements of B will be from, if it's present in B, it will be present in A. Okay. It turns out you can extend this idea to to vector spaces as well. So, and that's the idea of a subspace. Okay. Let's say we have a vector space V. Okay. We say, okay, this is our parent space, the bigger space. You say S is I don't know what the symbol is. For now, I'll just use this. S is a subspace of V if it satisfies two conditions. One, S is a subset of V, okay, and S is a vector space. Which simply means, S is contained within V, and S has to satisfy these two properties. Is that clear? Okay, now that's the definition. We'll look at some examples now again. Now, if our original parent space is R2, okay, is this a subset of R2? V? It is a subset, right? It's the first quadrant. Is there a subspace of R2? No, it's not. We just saw that does not form a vector space. So the second condition is not satisfied, so it's not a subspace. Okay, all right. What if I had something like this? So I'll call S equals A. Okay. S is a set of points. S is a subset of R2 because you've got two real numbers. Okay, such that the elements are A and K times A. Okay, where A and K are real numbers. Okay, what would this set look like if you were to draw it in R2? In fact, to make it simpler, let's say K is 1. There's no K. What would it look like in R2? Straight line, okay, like this. So this is R2, this is S. So it's clear it's a subset. Is it a subspace of R2? See, again, if you're not clear, this one is satisfied. You simply have to verify this. Blindly apply the rule. Blindly just verify these two. Why is it a vector space? If you take any point here, which is this vector, if you scale, when you do scaling, you don't change the direction. That means the new vector that you get by scaling this will actually lie on this line. Right? That means it will still be closed. I mean, S is closed in terms of vector scaling. Now, if I take two vectors, S1 and S2, if I add these two, I'll get another vector that is along this line. That means it's also closed under vector addition. That means this is in fact this particular form is in fact a subspace of R2. What if I had this, where K is also a real number? What would that look like geometrically? How do you go about plotting this? What is the role of K here? It's a slope, that's all, right? So it will either look like this, depending on the value of K, it can look like this. It will simply be some line that is passing through the origin. Okay, because the x-axis value is A, the y-axis value is simply K times A. So is this a subspace? If you had a subset of R2 like this, is that a subspace? I mean, when K was 1, we did find that it was a subspace. Now K is some arbitrary real number. It is, right? Now if you take any line that passes through the origin, it's closed under vector scaling and vector addition, so it is a subspace. So anything of this form is a subspace. Geometrically, in R2, any line that passes through the origin, any straight line that passes through the origin is in fact a subspace of R2. Okay, that's an important thing to remember. Okay, and then we talk about another example. Let's say our original space is Rn. Okay, and then my subset that I'm looking at is this. The set is simply the zero vector. Is there a subspace of Rn? Wait, this is clearly a subset of Rn. All you have to do is verify this. Is it closed under vector scaling? When you take 0, multiply it by alpha, it's still 0. That means it's closed. If you take 0 and 0 and add it, you get 0. That means it is closed. So this is what is called a trivial subspace of any vector space. Okay. Before we conclude, let me just we'll just see a few more examples of subspace. Okay. Instead of R2, let's say we're talking about R3. In fact, before that, okay, this is my original space. This is my subset S, okay, of R2. Is this a subspace? So all you have to verify is this closed under vector scaling and vector addition. Yeah. What do you think? No? Okay. You remember one of the things I said in the last class was for something to be a vector space, the zero element has to be there in that set. Does this have the zero element, zero vector? It does not. Does not pass through the origin. That means it does not have the zero vector. That means this is in fact not a subspace. Okay. But I will leave this as an exercise for you. So we could express lines that pass through the origin through a set definition like this. Okay. An exercise for you would be, what would be the corresponding set definition for this? Okay. You can try it yourself. So this will be some A1, A2, A, and there will be some condition on A1 and A2 to describe this set. Okay. I'll leave that as an exercise. So in R2, at least, only straight lines that pass through the origin are subspaces. Any other line, straight line that does not pass through the origin does not form a subspace. Okay. Another way to look at this is, okay, if you take any point on this line, any element from this subspace, right, that represents a vector like this. Right. Let's say we choose this point. That's this vector. Okay. What will happen if you scale this vector? It will reduce in length or it will stretch. That means it will move off the line. That means it's not in the line anymore. So it's not a it's not a vector. It's not closed under scaling. Okay. The same applies for vector addition. If you take two vectors like this, if you add them, the new vector is going to be somewhere here. It's not closed because you've left the line. Again, a circle. Let's say with radius 1. Again, I will leave it as an exercise for you to write the corresponding set definition for this circle. Similar to what I've written there, what would be the corresponding definition for the set here? That's an exercise for you. Is this a subspace? No, it's not. Zero is not there, so you don't have to worry. Okay. What about this? It's okay. Leave it like this. Okay. This is probably very easy because the zero is not there. What about this? Figure of 8. Zero is there here in the subspace. Or sorry, not in the subspace, in the set. Yeah, exactly. You take a vector here, you take this point that corresponds to a vector like this from the origin. If you scale this, it moves out of this shape. You're not there. Okay. Maybe you're seeing a pattern here. Okay, but before we conclude, let's say we now look at R3. Okay, not R2, but three-dimensional space. Now, I'll still keep it geometric. That way it's easier to. It turns out in R3 also, any lines that pass through the origin in the three-dimensional space will actually form subspaces of R3. Okay, that's one. But you also have additional subspaces in R3. Okay, any plane that passes through the origin in R3 will also be a subspace. Okay, in R2, the subspaces that you had were all lines that pass through the origin. When you go to R3, you have lines that pass through the origin that form subspaces, and you also have planes. Now, if you go to R4, right, you'll have lines, two-dimensional planes, and three-dimensional hyperplanes that pass through the origin. But the condition is all of them have to pass through the origin. And maybe the pattern that you're seeing here, so for example, if you compare these with what are subspaces and what are not, subspaces simply capture this geometric idea of a surface being flat. Okay, so linear algebra is essentially the study of surfaces that are flat. Okay, for example, lines, of course, and the additional condition they have to pass through the origin. Okay, lines are perfectly flat surfaces. Planes through the origin are perfectly flat surfaces. So in linear algebra, the kind of surfaces that we or kind of higher dimensional geometric structures that we are dealing with are completely flat. Okay, so that's another way to think about the geometric structures that we're dealing with when we're talking about vector space. Okay, I hope that's clear. And before we move on, right, I'll define one more term that we did not discuss before. See, if you have a vector space, right, and it's closed under vector scaling and vector addition, that also means that it's closed under another operation which is a combination of vector scaling and vector addition, which is called a linear combination. Okay, which is nothing but if you say, let's say you have two vectors v and w that come from some, for now I'll simply write Rn, from Rn. If you say you're taking a linear combination of two vectors v and w, all you're doing is you're taking v, multiplying it with some scalar alpha. We take w, multiplied by some scalar alpha 2, and then you add those two. Okay, and this type of an operation that you perform on two vectors is called the linear combination of vectors v and w. Okay, now you can extend this to any number of vectors that you want, any finite number of vectors that you want. It could be v1, v2, v3, so on and so forth to vm, all of which belong to Rn. If you say you're taking a linear combination of these vectors, all you're doing is you're taking the first vector, multiplying it by some number alpha, and then v2 for m vn. Okay, if you see these three dots, it simply means you continue this pattern. So alpha 1 v1, alpha 2 v2, dot 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 simply means alpha 3 v3, alpha 4 v4, so on and so forth, till you reach alpha m vm. This operation is simply a process of taking the linear combination of these vectors. Okay, another way to compress these two and express it in one sentence is, if you have a set V, it has to be closed under linear combination of its elements, then it's a vector space, otherwise it's not. Okay. 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 That brings us to the next idea, which is confusing at first, but it's extremely important. Okay. This idea of linear independence. Okay. Again, the definition might not make sense initially, but just remember it and just blindly apply. Okay. Let's say we have a set of vectors x1, x2, xm, let's say, all of which come from Rn. Rn is the vector space that we are dealing with. Okay. Now, let's say we take the linear combination of these vectors. What does it mean? It means I'm simply taking each of these, multiplying each of these by some number alpha, or alpha 1, alpha 2, and then adding the scaled vectors together. I will express that like this: I equals 1 to m alpha I xi. Okay. This is simply compact way of writing this. Okay, this represents a linear combination of these vectors x1 to xm. Okay, the definition of linear independence for a set of vectors is a set of vectors x1 to xm is linearly independent if this linear combination produces a zero vector. Okay, and the only linear combination that will produce a zero vector is if all the alpha i's are zero. If there is any non-zero alpha I such that this linear combination gives you zero, then this set of vectors is not linearly independent, it's linearly dependent. But if the only set of alphas that will, for which this linear combination is zero is if all alpha i's are zero, then you say that this set is linearly independent. Okay, we'll look at some examples first. Okay, we'll do R2. Okay, so we have two vectors, set of two vectors. These are both vectors from R2. Okay. Now the question is, I ask you, is this set of two vectors? Okay, I'll call that let's say W. Now the question is this set linearly independent? Okay. 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 Yeah, it is. Yeah, we'll come to see. We'll see why that is. Right. And how do you verify that? You verify that by first expressing taking the linear combination of these two. Okay. So you take the first vector multiplied by alpha 1 this is this. Okay. What will this give me? So this will give me alpha 1, alpha 2. Now the question is, when will this be equal to 0, 0? Right. So if you have two vectors like this, the only linear combination that will give me 0 is if both alpha 1 and alpha 2 were 0. Okay, because that's the only set of values for alpha is that will give me 0. This set is actually linearly independent. Okay, we'll look at another example. What if you had this? What will be the corresponding linear combination of this vector, of these two vectors? See, initially I would simply just write this down until you can do the arithmetic in your head without any problem. So alpha 1 times this, alpha 2 times this. Okay. And now the question is, when will this give me 0, 0? See, obviously, if you put zeros for all alphas, right, it will give you 0. But that's not enough. If there are other possible values of alpha 1 and alpha 2 that will also give me 0, 0, then it's a problem. Right. Now, if you choose, yeah, exactly. If you choose alpha 2 to be minus alpha 1 divided by 2, you'll get 0 for the first element and you'll get 0 for the second element as well. That means this set is not linearly independent. Okay, this is linearly dependent. Okay. We'll do one more and then we'll talk about the geometry of what this means. Is this linearly dependent or independent? Okay, you said dependent, you said linearly independent. Okay, what did you find? And then let's see if we can argue about it. This is how I remove this. Yeah. What did you do? Okay, When you take the linear combination, what do you get? So you did alpha I, xi. What did you get? Alpha 1 plus. Okay. Now, when can we get 0, 0? The trivial one is always there. If you choose all of them to be 0, you'll get 0. That's okay. Is there a non-zero value that you can choose for the alphas that will give me? Sorry. Okay, one of you, maybe you guys. Okay, so alpha 3 is minus of alpha 1. That will mean this is 0. But what with this? No, you can only choose one value, right? Alpha 3 can either be minus alpha 1 or minus alpha 2. Okay. Okay, alright. Fine. You are saying alpha 3 equals minus alpha 2. You can only choose one of these values. That means I can only make one of these elements 0. The other cannot be 0. Is that okay? Is the argument clear? The only way this will be 0 is if alpha 3 is minus alpha 1. The only way this will be 0 is alpha 3 is minus alpha 2. Both. It has to be one of these. But we are free to choose alpha 1 and alpha 2 though. What if I choose alpha 1 equals alpha 2? Then both are satisfied. That means there is a combination that I can find which will give such that the linear combination gives me 0. That means that set is linearly dependent. Okay, all right. What does all this algebra mean? Okay, see, one way to think about this is like this. Okay, R2. We take the first case. Where is the first vector for this? Where is x1 and where is x2? This is x1 for the first problem. This is x2. Right? We found that this set was linearly independent. Okay. For the second case, where were the two vectors? So, first vector x1 was this, x2 was this. Right? This was 1, 1. This was 2, 2. This was 0, 1. This was, 1, 0, 0, 1. This was linearly dependent. What about the third one? Third problem. So this is for the first problem. This is for the second problem. This is for the third problem. So you had x1, which is 1, 0. You had x2, 0, 1. And then you also had x3, 1, 1. Right? This was found to be linearly dependent. What do you think is going on? Let's forget about the third one. Let's look at these two. These two turned out to be linearly independent, whereas this turned out to be linearly dependent. So what do you think linear independence is saying in terms of the geometry of the vectors that we have in that set? Yes, yeah, you're too far ahead, but yes, that's essentially what. Yes. Or another way to put it is the two vectors in the second case are collinear, which is essentially what you're saying. It's you can get the other one simply by scaling the first one. Okay. So what we're seeing is linear independence then tells you something about if you. Okay, before I'll just point out one thing. When we say linear independence, right? Linear independence is a property. It's a property of a set of vectors. Okay, all right. Linear independence simply tells you that the set of vectors that you have, do they lie in the same? Do they point in the same direction, or do they all point in different directions? So here, the two vectors are pointing in different directions, and that definition there showed us that it is actually linearly independent. Whereas here, the two vectors in that set are not in fact are pointing in the same direction. So one way to think about this, if you think of the direction of the vector as something that is conveying some information, when we say a set is linearly independent, that means each element of the set is conveying slightly different information, or each of them contains slightly different information. But if they point in the same direction, that means there is redundancy in that set. The two elements are not independent of each other. Information in one is contained in another. So the two vectors pointing in the same direction kind of indicates that when you have that situation, then you say there is dependence between the vectors. Okay, and what type of dependence is this? Linear dependence, because we're talking about linear combinations. Okay, so that argument works well, at least for these two. Okay, but then do you think that's a complete argument? I'm saying if you have a set of vectors, all of whom are pointing in different directions, then I say they are linearly independent. Okay, that maybe applies for these two. What about this? They are in fact pointing in different directions, right? But when you do the test for linear independence, you find that they are actually dependent. Why is that? Why do you think that is? Yeah, exactly. Right? So the first two tells you that if you're in the set that you have, if one of the vectors is a scaled version of another set, that's it. You're done. It's linearly dependent. Okay, that is one condition. There is also another condition. If one of the vectors in that set can be expressed as the sum of two other vectors from that set, then also you have dependence. You don't have pure independence, because you can derive the third vector from two vectors from the original set. Okay. Now, combining both of these together, if you have a vector that is a scaled version of another vector in the set, no independence. If a vector is a sum of two vectors in the set, then also you don't have independence. So essentially what we're saying is, if you have a set and if there is one element there which can be expressed as a linear combination of any other vectors in that set, then that set is not linearly independent. Okay. If you have a situation where no element in that set can be expressed as a linear combination of the other elements in the set, then you say that then the vectors are linearly independent. Here, this set is not linearly independent because x1 plus x2 gives me x3. That means the information that is there in x3 is already there in x1 and x2, and if I simply do a linear combination, I can get x3. So that's why this is not independent. Okay, all right. If that's the case, then maybe we look at slightly more complicated example. Maybe example 4 from R3. Now, let's say we choose now I want to find out if this set is linearly independent. These are set of vectors from R3. Do you think this is a linearly independent set? Yes. I mean, if you simply apply the same logic here, you'll get alpha 1, alpha 2, alpha 3. The only way that will give you 0 is, okay. Okay, what about this? What about some? Is that dependent or independent? Dependent. Why? Exactly. So if you think of these two, this vector is along the x-axis, or the first along one axis. This is along the y-axis. The third point actually lies in the xy plane. Okay, that means if it lies in the xy plane, you can actually get by simply through the linear combination of these two. Okay, or another trick here is if you express the linear combination, right? Alpha 1, 1, 0, 0. Alpha 2, 0, 1, 0. alpha. So this will give you. No, sorry, I was thinking something else. No. Okay, okay. So that's clear. What about this? What if I had something like that? Is that set linearly dependent or independent? Independent. Okay, let's do the same thing as we did there. So you get alpha 1 times when will I get 0, 0, 0? What about alpha 3? Yes, 0, and that's always true. Is there a non-zero value for alpha 3 that I can choose that will still satisfy this equation? I can, right? If I choose 5, this will still give me 0, independent of what I choose for alpha. I mean, these two are 0 anyway, but I can choose any alpha 3. That means this is linearly dependent. Which means whenever you have a set that has a 0 element, you don't have to do any extra work. That is a dependent set. Okay, so 0 element cannot be there in a set, and the set can be linearly independent. Okay, right, right. The question is, when will this be equal to 0, right? If you express this, right, if you write it out, what will it be? It will be alpha 1 plus alpha 2 plus 0 here, nothing. So it will be alpha 1 plus alpha 2, or sorry, it will be alpha 1. It will be alpha 2. So when will this be 0, 0, 0? When these two are 0. What about alpha 3? I can choose any value for alpha 3 and this is still satisfied as long as these two are 0. That means this original condition is not satisfied. There is a non-zero value for alpha I that satisfies this equation. That means this set is linearly dependent. Is that clear? See, I don't expect you to get it. This can be confusing initially. If you simply go back and think this through, then it will start to make sense. Yeah. Okay. And that's what is stated here. I won't go into the details. Whenever you have a linearly dependent set, at least one of the elements in the set can be expressed as a linear combination of other elements in your set. That's what this expression says. But if you have a linearly independent set, you can never express one of the vectors as a linear combination of another. Okay. Okay. So that's okay. Okay. All right. We move on. The next idea the next idea is what is called the span of a set of vectors. Okay, I mean the idea is very simple. Let's say you have a set S of vectors v1, v2, vm, and for now we'll assume every vi is from Rn. Okay, the span of a set S is simply another set that has all the linear combinations of these vectors here. Okay, this is a set of all possible linear combinations of the original set of vectors that you have here. Okay? And that's what I sorry, this should be a plus. That's a mistake. Okay. So this will be, so you take any possible linear combination of these m vectors that will be present in the span of S. Okay, if that's the case, okay. Now the question is, these vectors originally came from Rn, which is a vector space. Okay, is this? Maybe we'll first look at examples before I ask. Okay. Let's say we're talking about R2, and the set that I'm interested in is 1, 1. Okay, this is my set S. What is the span of S? What all elements will that set have? So see, there is only one alpha 1, so V1, there is only one vector, so there will be only one alpha. Yeah, right. If there are R vectors, then it will involve linear combination of R of them. If you only have one vector, scaling is the linear combination of that vector. Okay, just scaling. Okay, so what will the elements of span of S look like? It will simply, so if this is V1, it will simply be alpha times V1, which means they will all look like alpha alpha. Is that clear? So in this case, the elements of where alpha is a real number. What about this?
by simply using the elements from S, I can reach any point in the span of S. Okay. Span of S tells me all the possible points I can reach by simply doing the linear combination of my original set of vectors. That's what it means to say then S spans the span of S. So that's again something to remember. And then the next idea, so we talked about addition of two vectors. It turns out you can also talk about the addition of two subspaces. Okay. That is already getting a little confusing, but anyway, once you spend some time with this, then it will start to make sense. Okay. Let's say we have Rn. Let's say we have two subspaces of Rn. And what does it mean? So two subsets of X and Y from Rn, which are also in turn vector spaces. That's what it means when I say they are subspaces of Rn. Okay. We can define an addition operation between two subspaces, and that's simply defined as a set of vectors which are the sum of two vectors X and Y, such that the X vector comes from the subspace X, Y vector comes from this one, which essentially means you take the sum of all possible combinations of vectors from the two subspaces, and that is the definition of adding two subspaces together. Okay. You can also show that if you add the two subspaces, what you get in turn is also a subspace. Okay. To maybe get a handle on that, right? Let's say we have two subspaces X, alpha, alpha. This is a subspace of R2. Okay, that should be clear why it's. We looked at an example like this. Then we have another subspace, S minus beta and minus beta. And both of these are subspaces of R2. Sorry, what will these look like if I draw them? What will the first subspace X look like? Please straight line like this. Because the first value is alpha, second value is also alpha. What about the second one? So this is the X. Second one would be like this. If the first value is 1, the corresponding first value is minus 1, the corresponding second value is will be minus of minus 1, which will be plus 1. That's here. The first value is 1, the corresponding value is minus 1. This is why it looks like this. This is why. Okay. Now, when you say that you're adding two subspaces, all you're doing is you take any vector from X, any vector from Y, you add them together, you get a point that goes into this set. If you do that for all possible combinations, you get the sum of two subspaces. What will be the sum of X and Y in this case? What will I get by adding these two subspaces X and Y? I'll get all of R2 now, and R2 is a vector space. So you can show that if you take the sum of two subspaces, the resulting set is also a subspace of your original vector space Rn. You can again extend this idea to three-dimensional space. You have X, Y, Z. If you have, let's say you have a set. You have a subspace R3. You have another subspace. We take the sum of these two subspaces. What will it give you? If you take the sum of these two subspaces, what do you get? Well, you won't get see. Okay, R2 is a different space. R2 and R3 cannot be compared. R2 is a set of two numbers. R3 is a set of three numbers. But your intuition is right. What do you get? You get. Imagine the first is the x-axis. First element corresponds to the x-axis. Second element corresponds to the y-axis. If you take the sum of these two subspaces, what will you get? The xy plane, right? So if you add these, if you take any element from here, and if you add them together, what you will get is alpha, beta, and 0. That means any value for the x value, any value for the y component, 0 for the x component, z component. That means you essentially get the xy plane. That's the idea. Again, why is this idea important and where does it really apply? Those you will see later on. But for now, just remember these things. It's died. Okay, all right. Again, those are all things you should remember because then it will make things that are coming later on a bit easier. Okay, so now those are mostly the definitions that we'll see a few more definitions later on. But before we go on, we look at a slightly different idea now, which is called the inner product. We finally come to something where we're talking about multiplying two vectors together. Okay? But it's a slightly different type of multiplication than what you would expect. Let's say you have two vectors x and y from R1. The definition of, okay, first the expression. If you say you're taking the inner product between two vectors x and y, the expression for that operation, inner product operation, is this x superscript b y or x transpose y. And what this means is you simply take the individual, so the vector x has elements like this. x1, x2, same. That's y1, y2, yn. When you say you're taking the inner product, you simply do this. You multiply the corresponding elements with the same index values. Okay? And you simply add the product of all these. Okay? It means you multiply xi with yi and you simply sum over xi with y. That's the definition. Now, what this means, we'll see later. Okay? This is a weird definition of multiplying two vectors. But it turns out this is a very useful operation. Okay? The definition will be slightly different if x and y are from Cn, but we will defer that for now. We will not talk about it. It's there in the slide, but I won't talk about it. Okay. And this inner product operation satisfies some properties. These again will be slightly different if x and y are from Cn, but if x and y are from Rn, then they will satisfy these properties. That means if you take the inner product of x with itself, that inner product will always be greater than 0 if x is not 0. And if x is 0, then the inner product will simply give you 0. And another thing to remember is this operation, I should also say standard inner product, which means there are also non-standard versions. Okay? This is a standard inner product. So the standard inner product takes two elements, okay, both of which are from Rn, and returns single real number. If the elements are from Cn, then this will be a complex number, but we will not worry about that. So that's the standard inner product operation, and it satisfies the first property where the inner product of a vector with itself can be 0 only if your original vector is 0. It's commutative, associative, and distributive. Again, these are things you simply don't worry. And in fact, from the definition, you can demonstrate that these properties are satisfied. So that's the inner product. Maybe you already know what the geometry is from physics. this is essentially the dot product between two vectors that we come across in physics. What is the dot product give us? It gives a scalar, but what is the geometric interpretation of the dot product? So if I have two vectors, A and B, what does A dot B give me? Right? But what is that? What is that number? Sure. It is used as a similarity measure, like the standard error product is used as a measure of similarity between two vectors. It's somehow related to the projection of one vector onto the other. Do you know? See, when will this dot product be 0? When 0 is 90. So this standard error product, that we will see, is related to the projection of one vector onto the other, and in particular, not any type of projection, but an orthogonal projection of one vector B onto another vector A. That is what is captured by this. And if that projection gives you 0, that means the two vectors are perpendicular to each other. And see, earlier I said when we talk about linear independence, right? If two vectors are in two different directions, they carry different information. But if you have two vectors that are almost pointing in the same direction but slightly different direction, then it should be intuitive that even though both of them carry different information, there is a lot of commonality between them. Right? That is essentially carried by the side. So if you have two vectors that are perpendicular to each other, then you say they are completely independent of each other in terms of the information that they carry. But if the inner product is not very small, then there is some commonality with the information that they carry. So that's essentially what is captured by this operation. So that's the standard inner product. And then the next important concept that you should know is the idea of norm, which is essentially a measure of this. Should not say size of the vector, because we already talked about size of a vector, which is the number of elements you have, or maybe the length of a vector. So that's what a norm is. Norm is a measure of the length of the vector. The norm that we are commonly used to is called the Euclidean norm. Okay. And that norm comes from the standard inner product. The Euclidean, so if you have a vector x, Rn, the Euclidean norm is written like this. So maybe you remember this from lecture 0, that we had terms like this when we were talking about fitting a linear regression model and all that. The Euclidean norm is represented like this: two vertical lines, the vector movement and the subscript. And this is nothing but x transpose x, and that, if you substitute that into that expression, that will come out to be. This we are already familiar with. Right? In R2, if I have a point here, what is the distance of this point from the origin? How do you measure the length of the distance of the point from the origin? Let's say this has values x, y. Right. This is nothing but using the Pythagoras theorem. It's essentially that extended to the nth dimension. Okay. If you're talking about vectors from R2, the Euclidean norm is exactly the formula that we use for measuring distances in a plane. If you have 3, then it's the same. How we measure distances in R3. Now, turns out that is not the only way to measure length. There are other ways to measure length as well. Okay? So this idea of the length of a vector in a vector space is a very general notion. Okay? See, for example, maybe this makes sense because that is what we've been taught from our high school. But it turns out there are other ways of measuring or defining distances that are also useful in applications. Okay? So this idea for norm is very general. So you say any function is a norm or is a valid norm, and the expression is two lines like this. And anything goes in, what goes in the center is any vector from Rn. You say that this is a valid norm function if this function takes an input from Rn and then gives out a single number that is always greater than or equal to 0. Because length does not make sense to have negative length. So any function that does that can be a valid norm or valid way of defining distances in a vector space, provided it satisfies these four properties. It means if the length of the zero vector is always 0, the length of any non-zero vector is always greater than 0, and if you scale the vector by some number beta, the corresponding length gets scaled by beta. And then the last one is essentially what is called the triangle inequality. It means the length of the sum of two vectors is always shorter than the sum of the individual lengths of the vector. That means if you have a triangle, this is x, this is y, and this is x plus y. The length of one side is always smaller than the sum of the lengths of the other two sides. That's what this captures. Now, the reason that is there is because you can have situations where that is not satisfied, which will correspond. This can happen in non-Euclidean geometry where this condition is not satisfied, but we don't have to worry about that. If you're talking about vector spaces, this triangle inequality has to be satisfied. So if you have any function that satisfies these four properties, then that is a valid way of measuring distances. I'll just finish this and then we'll stop for the day. So that brings us, so when we started talking about the Euclidean norm, which is how we normally measure distances in space, we had an expression like this with subscript 2. That should already have told you maybe there are other versions to this as well, and those are what are called P norms. Okay? And the P norm is defined like this. If you have a vector x, the P norm is simply you take the individual elements of this vector, take the absolute value, place it to the power P, add all of those elements, and then you take the P through. Okay? And here P has to be integer and P is greater than or equal to 1. It turns out any expression like this or any formula like this satisfies all those properties, and they are all valid ways of measuring norms. And what I'm showing here are what the set of points will look like, such that all of them have unit P norms. Okay? Let me just clarify and then we'll stop. The second one we are familiar, right? For example, let's say we are talking about R2. If I ask you what are all the set of points in R2 whose Euclidean distance is 1, what would you tell me? Where would you say the points would lie? It would be a circle, right? So these are all points such that the 2 norm is some number R, where R is a positive real number. Now you can ask, okay, is what is the corresponding geometry for or corresponding shape for the different p norms. Now, if you look at, I've only shown. Okay, we'll first look at the two popular ones, and then we'll look at the last one. We look at the first norm. According to this, what is the definition of the first norm? What will it be? P is 1, this is 1, so that means there is no rooting operation that you do. So it's simply the sum of the absolute values of the elements of the set. Right? Simply I. It turns out, now you can ask, okay, what is the set of all points whose first norm is 1? It turns out that will simply be a diamond of this square diamond. You can think about why that is. And funnily, there is also an infinity norm, okay, which is, it looks strange compared to the definition. The infinity norm is simply, you take the absolute value of all the elements of your vector, and then you choose the one with the maximum absolute value. For example, if I have a vector like 1, minus 1, 3, the infinity norm of this vector, what would it be? You take the absolute value of each element and you choose the maximum element. It will be 3. If you had a vector like this, the infinity norm is still 3. Okay. It turns out that this is actually not that different from the P norm. This is simply the limiting case of that norm. Okay, you can think about what will happen if P tends to infinity. When P tends to infinity, you will find that is actually this. And the geometry associated with the infinity norm is simply the square. So if you can ask, what are all the points in R2 such that their infinity norm is 1? It turns out it's simply the square. This is 1, 1. Now you can see the trend, right? One norm looked like this, 2 norm was the circle, and the infinity norm is like this. Where do you think the peak norm will be? There will be some finite integer, positive integer. It will be somewhere in between a square and a circle, and that's what I've shown here. So as you increase the value of p, this circle will essentially tend towards the square. That's what is shown here. Okay, with that we'll stop for today, and then on Thursday I'll complete the rest of the lecture, and then we'll go through the tutorial problems for this. Are there any questions before we conclude? Okay, so please go through the material. There is a lot that we discussed today, and maybe initially these things might sound a little confusing, but once you look at them regularly, it becomes a little bit more easier to deal with.